Okay, thanks everybody for tuning in this week. We're very happy to have Professor Berti speaking today. He's a world expert on black hole quasi-normal modes, and today he's going to discuss black hole spectroscopy. So please take it away.
Thank you so much for the invitation. And sorry, I've been told that there is not a strict 1 hour limit on the talk, so I'll try to move relatively fast. This talk is supposed to last less than 1 hour, but feel free to stop me at any time and ask questions. I'm sorry. So let me give you a little outline of what I'm going to discuss today. First of all, I will start with an introduction to the history of the field, especially for those of you who don't work on black hole quasi-normal modes and the like. And I will describe how it developed from a purely theoretical problem related with the existence and stability of black holes to experimental science. In the second part of my talk, I'm going to discuss in particular issues that have become particularly pressing now that we have to confront theory with data. And these issues are related with the role of overtones, whether we can extract them reliably from numerical relativity waveforms, whether nonlinearities play a role in the merger at all. It has been questioned, and I will argue that I do still think that they do play an important role. And the elephant refers to the question whether we are abusing linear theory in fitting merger waveforms with linear black hole perturbation theory. Then I will turn to another very hot topic, which is whether we have already observed overtones in existing gravitational wave signals. There's been a controversy, and I will describe where the controversy comes from and what I think about it. And in the last part, if I have some time, I will describe another hot topic that has emerged recently, which is the issue of stability of the black hole quasi-normal mode spectrum itself. People have started using techniques borrowed from other fields, in particular the notion of pseudo spectra, to understand whether the quasi-normal mode spectrum is stable or not. And they found that it's not. And maybe this plays a role in all of the experimental confrontation between the theory of black hole quasi-normal modes and the data. Okay, so let me start, as I promised, with a little overview of the field as it developed historically. I'll start from the very beginning. The very beginning is the discovery of the Schwarzschild metric soon after the formulation of the Einstein field equations by Einstein. As you all know, for the longest time, it was unclear whether this metric was physical or not, because it seemed to have two singularities, one at r equals 0, one at the Schwarzschild radius. Now we understand that the singularity at the origin is actually a physical curvature singularity, but the one at the Schwarzschild radius is removable. It's a coordinate singularity. And the key questions for the longest time were whether this Schwarzschild singularity had anything to do with physics, in particular, whether it represented the endpoint of gravitational collapse. A breakthrough in this sense was the 1939 paper by Oppenheimer and Snyder that answered the question affirmatively, but under very restrictive assumptions. Oppenheimer and Snyder studied the collapse of dust, a pressureless matter in spherical symmetry, which of course is not a realistic model for a collapsing star. And in fact, in the 1960s, Lifshitz and Kalatnikov argued that the formation of singularity was not a generical outcome of collapse. John Wheeler, returned to this question in the 1950s and 60s. And in particular, the question became particularly pressing following the discovery by Schmidt of a quasar, what we now understand is a supermassive black hole. And the question became, are there physical reasons why the collapse would halt and not lead to the formation of a singularity? And of course, all of the work on the equations of state with the help of nuclear physics experts ended up concluding that indeed, quantum mechanics is not enough to halt the collapse. The final answer to this question came from the use of new mathematical tools that were introduced by Penrose and Hawking and led to the famous singularity theorems that say essentially that, yes, the Schwarzschild metric is generically the outcome of gravitational collapse. Then, of course, the second question, once this first issue was resolved, was whether the solution is stable, because in physics, if you have a solution, you want to make sure that it is physically stable. And the answer to that question came from black hole perturbation theory, the theory of quasi-normal modes, and eventually led to what we call black hole spectroscopy now. So, like I said, the answer to the first question came from the Hawking-Penrose singularity theorems that established that the formation of singularity is inevitable as long as there is a trapped null surface and suitable energy conditions are met. And the development of the theory of black hole perturbations happened mostly during the 1950s, 60s, and 70s. So a crucial year in the development of this story is 1963, when famously Roy Kerr discovered a mathematical solution that describes rotating black holes. This brings black holes closer to the realm of astrophysics because everything in the universe rotates, so you want to have a solution with angular momentum to describe the endpoint of gravitational collapse. And then on the observational side, like I said earlier, Martin Schmidt at Caltech discovered the first quasar, and Giacconi and Gursky proposed orbital satellites to study X-ray sources and famously discovered Cygnus X1, which is the first stellar mass black hole. So stimulated both by these theoretical and observational developments in the 1960s and 70s, Kip Thorne and his group kickstarted what Kip in his popular books likes to call the golden age of black hole physics. And together with his students, in particular Saul Tiulkowski, they laid the foundations for black hole perturbation theory and to understand black hole stability. So one of the cornerstones of the development of black hole perturbation theory is the formulation of the perturbation problem in terms of a scattering problem. This is due mainly to Regge and Wheeler and Zerilli. Regge was a postdoc working with Wheeler, and in the 1950s, 1957, he managed to formulate the problem of odd parity perturbations of a Schwarzschild black hole as a scattering problem. Basically, what you do is you separate out the time dependence using a Fourier analysis, and you separate out the angular dependence using tensor spherical harmonics, and you discover that you are left with a problem that involves only the radial coordinate. And in the case of odd parity perturbations, what I call V minus here, you have a Schrödinger-like equation. There is a Schrödinger-like equation once you identify omega squared with the energy, and FDDR is your tortoise coordinate, derivative with respect to the tortoise coordinate. So in this scattering problem, what you have is that you need to solve a Schrödinger equation with certain boundary conditions. The boundary conditions were not understood at the time when Regge and Wheeler formulated the problem in this way. It also took a pretty long time, about 13 years, for the corresponding problem under polar parity to be resolved. And it took so long because the polar equations are much more complicated. The problem was solved by Zerilli only in 1970. What Zerilli found remarkably is that also for polar gravitational perturbations, you end up with a similar problem. It's just that the form of the scattering potential is more complicated. But remarkably, as Chandrasekhar will discover a little bit later, both potentials yield the same quasi-normal mode spectrum. I will explain what this means in a minute. Just as an aside, also scalar and electromagnetic perturbations can be formulated in the same way with potentials that take a similar form. So the next step in understanding what's going on here came with the work of Vishweshwara, who decided to investigate this problem. First of all, he understood the boundary conditions, which was a critical issue. And then he studied the problem purely numerically. What he did was he took a perturbation represented by a Gaussian wave packet, and he scattered the Gaussian wave packet on this potential. And then he looked at the response of the black hole. This is very similar to a quantum scattering problem of a one-dimensional potential barrier. And what he observed was that at infinity, the waveform looks like a damped exponential. So he repeated the experiment using different forms for the Gaussian and so on, and this seemed to be a generic outcome. Later on, Press understood that in fact, what Vishu observed and called ringdown waves, because they are similar to the damped modes that you can hear when you strike a bell with a hammer, these ringdown waves are nothing but the free oscillation modes of the black hole defined by imposing suitable boundary conditions. And soon after, Davis, Ruffini, Press, and Price realized that these free oscillation modes of the black hole are excited by studying the simplest possible physical process that can disturb a black hole, which is the case in which you take a particle and you dump it radially into the black hole. And what they saw was that the energy spectrum observed at infinity in that case grows. This initial growth is basically just the radiation emitted by the particle as it falls in. But then at some point, there is an exponential cutoff in the energy spectrum, the energy per unit frequency. And this exponential cutoff happens exactly at the frequency of oscillation that Press had identified and that Vishu had observed through the scattering experiments. This happens for all of the modes with different values of L, different angular harmonics. The next crucial step was the development of a similar formalism for rotating black holes that happened through the work of Tucholsky in the early 1970s. Now, the first calculation of the whole spectrum of black holes was attempted, and not completely successfully, by Chandrasekhar and Detweiler in 1975. They just tried to integrate the scattering equation numerically, and they managed to compute a few of what we now call the overtones of the Schwarz geometric modes with a larger imaginary part and a smaller damping time. But very significantly, already in 1978, Cunningham, Price, and Moncrief managed to do simulations of collapse in black hole perturbation theory that were more realistic in many ways than the ones done by Oppenheimer and Snyder. And what they observed is that not only the fundamental mode of black holes was observable in the spectrum, but also the overtones, these higher modes for a given value of L. And here you see a plot from the Cunningham, Price, Moncrief, where what they do is they fit the first damped exponential to the spectrum, then they subtract it, and they see that the remainder also looks like a damped exponential with the right frequency and damping time. The calculation of the Kerr spectrum was first completed by Detweiler that you see here. And already in his 1980 paper, where he first computed the whole spectrum of Kerr black holes, he said at the end of the paper, after the advent of gravitational wave astronomy, the observation of the black hole's resonant frequencies might finally provide direct evidence of black holes with the same certainty as, say, the 21-centimeter line identifies interstellar hydrogen. So it was very clear in Detweiler's mind already in 1980 that if you could observe the frequencies and damping times of these oscillation modes of black holes, you could use them very much in the same way as you use spectral lines in atomic physics to identify the objects that you are observing as Kerr black holes. Now, let me explain a little bit. I've been talking about these boundary conditions for a while, but let me explain what I meant. If you look at the generic shape of these potentials that I have shown you earlier, they always look pretty much the same. They go to zero at the black hole horizon. They have a peak, which is located very close to the location of the light ring, and then they go to zero at infinity. The boundary condition at infinity will change if you consider perturbations induced, for example, by massive fields, but I will not discuss this case at all, even though it leads to a lot of interesting phenomenology, including superradiance, hydrogen-like unstable bound states, and so on. So I will focus on quasinormal modes. What are quasinormal modes? Quasi-normal modes are solutions to the one-dimensional scattering problem that satisfy the boundary conditions that you have only ingoing waves at the horizon of the black hole and only outgoing waves at infinity. When you impose these two boundary conditions, you get an eigenvalue problem that you can solve. And it turns out that the only solutions of your scattering equation that satisfy these boundary conditions correspond to a discrete set of complex frequencies that are called the quasi-normal modes. Now, if you do this using either numerical or analytical methods, what you discover is that the spectrum looks like so. Take the dominant mode for gravitational perturbations. Because gravitational radiation is quadrupolar, the dominant mode is going to be the L=2 mode. And what you will discover is that the spectrum looks like the red dots here. You have a mode with small imaginary part down here. This is called the fundamental mode for L=2. And as you go to higher and higher imaginary parts, you get modes with lower and lower real part of the frequency until you hit the imaginary axis with something called the algebraically special mode, which is a whole separate topic that I will not discuss. And then the spectrum keeps growing like so and approaches a constant value of the real part of the frequency as the imaginary part goes to infinity. If you look at the spectra for other values of L, it looks similar, but the frequency, the typical frequency of oscillation of the fundamental mode is larger. Using WKB arguments, you can realize that roughly the frequency is proportional to L or to M. Now, this is true for Schwarzschild black holes. What happens if I consider a Kerr black hole? If I take this mode and I now look at a black hole that is rotating with a Kerr parameter A, what happens is that basically you have a Zeeman splitting of the spectrum. And so for any given L, you have 2L plus 1 allowed values of the quasi-normal mode frequencies from m=2 to m=-2. And for each of them, you have a different spectrum that now depends both on the mass and the spin of the black hole. So the key idea of black hole spectroscopy as formulated by Detweiler is, suppose that I know that I'm observing the L=m=2 mode. If I measure the real part and the imaginary part, because this number is uniquely fixed by general relativity, I can measure both the mass and the spin. Now, say that I observe also this other mode. This is called spectroscopy with higher modes. Because the frequency and the damping time are fixed in general relativity, by measuring this other mode, I'm going to have a test of general relativity. Of course, I can do that test either by observing overtones, higher imaginary parts for the same L, or by observing different values of L. But what matters is that these values are consistent with the predictions of GR within the linear theory. Now, the question, if you want to do this in practice, is how much are these modes excited? And at the time of Detweiler, or even before 2005, we couldn't answer this question simply because we didn't have numerical simulations of the merger of two black holes. And the situation changed after the numerical simulations, but notably, even before then, people observed that the overtones are excited by doing several numerical experiments. For example, Ferrari and Ruffini studied ultra-relativistic infalls of particles into black holes, and they noticed that the overtones were excited. Stark and Piran in 1985, very early on, managed to simulate rotating collapse, and they found that the overtones of Kerr black holes were excited in simulations of rotating collapse. And later on, this study of excitation made a lot of progress, mainly through the work of Lieber. Now, this is important, and let me explain a little bit what's going on here. What Lieber did was he studied the Green's function corresponding to black hole perturbations in both Schwarzschild and Kerr. And what he understood is that to compute the Green's function of that radial wave equation that I was showing earlier, you need to compute an integral in the complex plane. This integral consists of three main parts. One is a contribution from the large semicircle here. That part is called the prompt response. It's basically a large frequency or small time perturbation that corresponds to the gravitational radiation emitted by, say, a particle as it falls radially into your black hole, what I was showing you earlier. Then there's a second contribution to the integral that comes from a branch cut, which you see over here. That part is called the late time tail. And then there's a third contribution to the integral that comes from the residues associated to the poles within the integration contour. That part are the quasinormal modes. And you can also, using this formalism, compute the amplitude of excitation of the modes. Lever did this work. Anderson did it using different techniques. And later on, we extended it to the case of Kerr black holes to compute the excitation. But in the meanwhile, there was also a lot of heuristic work that noted, in particular this paper by Flanagan and Hughes, that in a realistic merger, the typical signal to noise ratio that you would expect from so imagine that you have two black holes that come together and merge. Most people up to that point have been focusing on the radiation emitted during the spiral, but Flanagan and Hughes reasoned that it was quite likely that the energy emitted in the ringdown should be about the same as the energy emitted in the spiral. And this idea of black hole spectroscopy resurfaced in 2003. There was a lot of interest in this topic, as Shahar knows very well, because there was a conjecture that quasi-normal modes may be related with ideas on area quantization. I will not go there. But basically, people started reconsidering this idea, and we wrote a pretty long paper in 2005, where we tried to understand the typical signal-to-noise ratios and the measurability of these modes. As I said, the understanding of how much these modes are excited changed in 2005 when Franz Pretorius finally managed to simulate two black holes coming together and merging. And soon after the simulations, Bonanno, Cook, and Pretorius analyzed the waveforms that were produced by Franz. And this is what they found. Now, it doesn't matter what is plotted here, but it's basically the waveform. And what you see is that if you try to fit the waveform with only the fundamental mode, one single damped sinusoid, you get a very good match with the black curve that corresponds to the numerical simulation. Then what you can do is subtract the red line, the fit with a single damped sinusoid, from the full waveform and look at what is left over, the residue. And you see that the residue looks again like a damped sinusoid. So you can fill it again with the first overtone, and you will find that the next residue is going to be smaller, but it still looks like a damped sinusoid and is closer to the peak of the waveform. So you can repeat this procedure and you can fit multiple overtones to the ringdown. But if you look at the paper by Bonanno, Cook, and Pretorius, they said, well, okay, you can do this, but it doesn't mean that it's physical. We don't know whether linear black hole perturbation theory is valid all the way to the peak. And in a similar paper in 2007, we quantified the excitation of the higher multiples, the ones I was talking about before. And later on, other people improved on the initial studies that we did by using Bayesian methods and so on. Now, of course, the next breakthrough came in 2015 when we had an actual observation. And I remember receiving this paper from PRL and my jaw dropping because the shape of the waveform that you could see in the original GW150914 detection looked pretty much exactly the same as the waveforms that have been computed by Pretorius and others using numerical relativity. So the question is, if you look at this data, these are the LIGO-Hanford data, these are the LIGO-Livingston data, do you have enough signal-to-noise ratio to clearly see a damped sinusoid in the data over here? And in the original LIGO papers, what they said was, yeah, well, maybe you can see one damped sinusoid here in the late part of the data with a signal-to-noise of about 7. But later on, there were claims that you could analyze this data and actually observe also the higher overtones. So one of the questions that I will address later on in this talk is that true? Have we done it? It's clear that sooner or later we will do this. So what you see in this plot is the noise power spectral density of gravitational wave detectors now and in the future. At higher frequencies here, what you see is the typical noise power spectral density in LIGO 01, the first observing run, the second observing run, and the sensitivity that will be achieved when advanced LIGO reaches what is called the design sensitivity. So this is basically everything above these curves is observable. And if the curves go down, it means that you're going to see things better and you're going to see more events. Every time you double the sensitivity, you increase the number of events roughly by a factor of 8, because the sensitivity goes with the cube of the amplitude of the gravitational waves. The number of events does. So what you see here is that as we increase the sensitivity, sooner or later, we're going to have a high enough sensitivity to observe the ringdown with much higher SNRs than the value of 7 that we had for the first event. And in fact, with the best detectors that we can build in the LIGO facilities, we're going to have much higher sensitivities. And we're going to do even better with future facilities like Cosmic Explorer and the Einstein Telescope. The LISA noise curve that you see over here may look much worse at the beginning until you realize that the signal to noise in the ringdown scales with a power of n to the 3/2. So if you go down by 4 orders of magnitude in frequency, correspondingly, you go up by about 6 orders of magnitude in the mass scaling. And so the typical SNRs that you will see in LISA will usually be much higher than the ones that you see in LIGO. And this is why in a paper in 2016, soon after the first detection, we forecast that with a Voyager class detector, the best that you could see, that you can build in the current LIGO facilities, you should start being able to do black hole spectroscopy routinely. And with LISA, you will do it pretty much with every detection. These results were confirmed later, for example, in this paper by Ota and Cirenti, where they did more refined calculations, but they similarly showed that if you take the sample of LIGO events, you can only do black hole spectroscopy when you are within what they call redshift horizons. And so with LIGO, you cannot do it, but as you build better and better facilities, you will be able to do it. And this is the result for LISA. Let me explain. What you see here with the solid symbols are how many detectable events you're going to have every year. These, of course, are based on some astrophysical models that I will not discuss. And the empty symbols show you how often you will be able to detect more than one mode and therefore do tests of general relativity. And the number of events is much smaller because you need to see more than one mode. Now, all of this was challenged recently because people claim that, in fact, you don't need to worry so much. You can use linear black hole perturbation theory all the way to the peak of the waveform. Let me explain what the argument was and why I do not quite believe that this is a conservative point of view. First of all, let me go back to basics. Suppose that you go back to the Vishveshwara experiment and you take a Gaussian, you scatter the Gaussian on a black hole, and you obtain a waveform that you see down here. And then you want to fit this waveform with a single damped exponential. So this is the simplest possible experiment that you can make. What you see here in this animation is the starting point of the fit. And the curve that you see in red is the fit that you get with a single damped sinusoid. So by doing that fit, you get a certain real part and a certain imaginary part. We know exactly, we are in linear perturbation theory, there is nothing weird going on here, that the real frequency and damping time should be here. But as you change the time of your fit, as you can see, the fitted real and imaginary part of the frequency is initially very different from the value that you would expect. And it only approaches the real value through this very strange behavior at pretty late times. How late? Well, maybe something like 10M or 15M after the beginning, okay? So you can repeat this experiment with 2 modes, because that's the test that you want to do. You want to observe 2 frequencies. Now, you see what happens if you repeat this test with 2 modes. The first converges pretty well, as you can see also over here, to the value expected from theory. But the first overtone doesn't do what you would expect it to do. It's coming in from over here, and it flies around the right value of the frequency that you would expect and then goes out. So even in linear perturbation theory, in the very simple setting where you're scattering a Gaussian, it's very hard to recover the frequency of the first overtone. Okay? It's even worse if you try, well, you may say, okay, I may want to fix the frequency of the fundamental mode and then fit the first overtone. The same thing that happens. You only go through the expected value, but then you fly out again. And things get even worse when you try to fit higher overtones. Here, you are fixing the fundamental mode and the first overtone, and the second one doesn't even get close to the value that you would expect. Okay, so what's going on here? Well, we know from the theory of Green's functions that if you had the right frequencies, then you're going to get a better and better fit of the waveform. This was demonstrated by Lieber first, using particles falling radially into black holes. It showed that if you include more and more overtones, you're going to get a better and better fit of the waveform at earlier and earlier times. And then we extended that work to Kerr black holes over here. However, the importance of overtones for full numerical relativity was not quite appreciated for a while. And we wrote a paper back in 2017 with my student Vishal Baibat, where we said, can you recover the mass and the spin, or even the frequency and the damping time of the fundamental mode, if you fit the waveform by a single mode as was done by LIGO? The answer is no. So let me explain what you're looking at here. We take a numerical relativity waveform, state-of-the-art waveforms computed by the Caltech group, and then we try to recover the real and imaginary part of the fundamental mode by fitting only one damped exponential to the numerical relativity waveform. There is no noise here. So what you see is that the real part is measured better and better as you fit at later and later times, but you always get an accuracy of at best one part in 100, maybe 1%. And for the imaginary part, you do even slightly worse. However, you can do better if you include more modes. So the error on both the real and the imaginary part decreases a little bit, and it decreases even more if you include the next overtone. The behavior is kind of weird, but the errors get better. And the errors on the real and imaginary part can be translated into errors in the estimate of the mass and the spin. So your estimate of the mass and the spin, as you see in the bottom plot, also gets better when you include overtones. So we were arguing, if you want to look at both numerical simulations and data, you should include the overtones. So the Caltech group took this idea and kind of—
Can I ask a quick question?
Yeah,
please?
sure.
So I know these quasinormal modes are not complete, but if you have 7 overtones, I mean, at some point, can't you just fit any decaying signal better and better? I mean, you know, you could get some waveform and say, if I allow myself to have 100 overtones, then I can get a perfect fit.
Totally,
In some
totally. That's where I'm going.
So,
That's where I'm going. I'm going to tell you more about this. I completely agree with you. Okay, in fact, what Alex was asking is what I'm showing here. So what have the Caltech group done, Giesler and others? What they said, well, okay, why don't we throw all of the overtones into the mix, okay? And if you throw all of the overtones into the mix, you can compute a number that is called a mismatch. Think of the mismatch as a scalar product between your model Ringdown waveform that is obtained by superposing n overtones, where n goes from 0, so this means only the fundamental mode, to fundamental plus first overtone, 2, 3, 4, and so on. And then they compute this number that is called the mismatch. If the mismatch is small, it means that your superposition of quasi-normal modes is a good fit, in this case, to the L equal M equal 2 component of the full merger waveform. And they said, look what happens, it's amazing. The fundamental mode gives you a pretty bad fit at early times, but then you include one overtone and you do better. You have a minimum here. You include 2, you move your minimum here. You include 3, 4, 5, 7, and your minimum mismatch moves all the way back to the peak of the full waveform. And they jumped to conclusions, I believe, and they said, this is a quote from their abstract, including overtones allows for the modeling of the Ringdown signal for all times beyond the peak strain amplitude, indicating that, bold-faced mine, the linear quasi-normal regime starts much sooner than previously expected. Previously expected was something like 10M. That was what Buonanno, Cook, and Pretorius, for example, found. This implies that the spacetime is well described as a linearly perturbed black hole with a fixed mass and spin as early as the peak. I beg to disagree, like Alex did, and I will explain why. So let me give you a couple of physical arguments why I think this cannot be correct. The first is that other people have tried to do a similar game by adding what are called the counter-rotating modes. There is a symmetry in the quasi-normal mode spectrum where you can take positive frequency modes and negative frequency modes, and they are symmetric under a certain symmetry. And what happens is that if you add the counter-rotating modes, then you can do exactly the same thing. This is the same plot taken from a paper by Satya and collaborators, Arnab Dani and others. And you see that as you include the counter-rotating modes, your fit gets better. And in fact, you can get a very good mismatch before the peak. Now, this is physically unreasonable. This is just fitting additional modes that shouldn't be there, because we know from black hole perturbation theory that you can only excite the counter-rotating modes when you have counter-rotating orbits. And this fit refers to simulations that have either no spins or aligned spins. So you shouldn't get a better fit, but you still do. So the argument is, yes, as you make your fitting function more and more complicated, you get a better fit, but that doesn't mean that you are adding meaningful physics. Another argument goes back even earlier. This is a simulation from 1996 using nonlinear black hole perturbation theory. We didn't have numerical relativity at the time. What people did was they looked at head-on collisions of black holes, and they simulated them using linear black hole perturbation theory and nonlinear perturbation theory. And what they found was that the waveforms in nonlinear perturbation theory were different. So there should be some nonlinear effects. Admittedly, the amplitude that they found depended on the initial data. But if you see nonlinear effects in a head-on collision where the energy radiated is extremely small, you should see nonlinear effects even in non-head-on mergers where the nonlinearity should be much more important. In fact, if you look more carefully at the paper by Gisler and others, you start noticing that something is not quite right. So what you see here is the fitted amplitude of the fundamental mode, and then the fundamental mode plus the first overtone, and then the fundamental mode plus the first overtone and the second overtone, and so on. And now look at the fitted amplitudes of these modes. The fundamental is doing pretty well. The amplitude is constant to within 3 decimals. But the first overtone changes quite a bit when you add the first overtone. The second overtone. And it stays roughly constant, but not to the same level of accuracy. Now, things go pretty bad when you start adding more and more modes. The amplitudes change a lot. Notice also that the time at which you get the optimal fit is also different, okay? So the question is, why are these amplitudes changing so much? Is it really true that we can trust linear black hole perturbation theory all the way to the peak? This same observation, I'm not the first to make it. It was made by many people following this paper by Gisler and others, including Swetha Bagua, Pierre Mourier, Hisco Jimenez Forteza, Laura Sbern, and many others. So let me show you. My argument is very similar to what an argument that was made by Freeman Dyson. You probably heard this story before. Freeman Dyson had, at the time, people were looking at meson proton scattering. And Enrico Fermi had data, and Dyson had a model that fitted the data very well. So he went to visit Enrico Fermi in Chicago with his students, and he said, you know, you can read this story. It's reported in a very nice paper by Dyson in Nature. He said that when he showed the data to Fermi, Fermi said, it barely looked at what Dyson was presenting, and he said, there are 2 ways of doing calculations in theoretical physics. One way, and this is the way I prefer, is to have a clear physical picture of the process that you're calculating. The other way is to have a precise and self-consistent mathematical formalism. You have neither. And Dyson says, in desperation, I asked Fermi whether he was not impressed by the agreement between the calculated numbers and his measured numbers. And he replied, how many arbitrary parameters did you use for your calculations? I thought for a moment, says Dyson, about our cutoff procedures, and I said 4. And Fermi replied, I remember my friend Johnny von Neumann used to say, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And with that, the conversation was over. Dyson was crushed, but later on, he would thank Fermi because basically what was happening is that he was missing the quark model. And so they didn't have a complete theory at the time. They were doing phenomenological fits of the data, and they thought that the agreement was good, but it was a coincidence. So what happens here? There's a question of completeness. I think Alex was pointing it out. So people may get back at me and say, well, you're not getting a constant amplitude. In fact, I had this conversation with Soltyukowski, and he said, you cannot get a constant amplitude because you have a problem of completeness. So let me simplify the problem, and let me say, I don't want to worry about completeness. I'm going to make a very simple model where I take 4 damped sinusoids, and I try to fit them with damped sinusoids. In this case, my model is damped sinusoids. Sorry, my signal is damped sinusoids, and my model is damped sinusoids. And what you get if you fit damped sinusoids with damped sinusoids are constant amplitudes. This is shown with the dashed lines. No surprise there. Now, try to add a little non-linearity to your signal, for example, by using a Gaussian at early times, superposed to your damped sinusoids. What do you see if you try to repeat the fit? Well, what you see are the solid lines. If you fit with 4 damped sinusoids, a signal that contains more than 4 damped sinusoids, the first few modes have a very constant amplitude, but as you go to higher and higher overtones, you start seeing some weird behavior at early times. And at late times, however, you're doing well. And the reason is that the nonlinearity has decayed, and you are still getting a pretty good fit by adding only linear damped sinusoids. And you can repeat the experiment with more and more modes, and you see the same thing. So what's going on? Let me go back to the Gaussian experiment that I was doing at the beginning, the Vishu experiment. If you do that experiment, you remember that we couldn't recover the frequencies very well. But let's assume, like the Caltech group, that we know the frequencies. Now, in terms of doing spectroscopy, this is a very big assumption because you're assuming that all of the frequencies depend on the mass and on the spin as predicted by GR. So you're not doing the same consistency tests that we wanted to do in the beginning. You're doing a weaker one. But if you do this, what you find is that the amplitudes of the fundamental mode is very well constant as long as you are, say, 10M after the peak. Then you add the first overtone and you see that the fundamental mode has a constant amplitude. The first overtone, not quite as much. This is consistent with Gisler and others. But there is a window that we highlight in yellow here, where both the first mode and the overtone have a roughly constant amplitude. And then you can increase the number of modes. And that window basically moves to earlier times and shrinks. Okay, this is in linear perturbation theory. So let's repeat the same analysis on the numerical relativity simulations that were studied by Gisler and others. Same thing, you see. First, you fit with only one damped exponential, and you get that the frequency, the amplitude of the fit is very well constant at times larger than about 10M. But the claim by Gisler and others was that you could push everything to 0, not 10M. And when you add overtones, you find that the amplitude of the first overtone is roughly constant, but not at 0. It's constant after 12M. This line highlights where the amplitude is constant within about 10%, the shaded region. And that's what it does. Then you add a third mode, and you see that the region where the amplitudes are approximately constant is shrinking, and you can repeat the game and you understand where I'm going. If you add more and more modes, you can fit all the way to 0, but you're not doing physics anymore, you're overfitting. You're adding more and more modes with amplitudes that are only constant in an infinitesimally small region. And in fact, you can plot the region in which the amplitudes are constant, and it is shrinking to 0. Here you see exactly the region in time in which the amplitude is constant within 10%. And as you add 7 modes, there's no time at which the amplitudes are all constant. Okay. So I think this pretty much closes the argument that you can do the fit with linear modes. Alex?
Emanuele, so this was very interesting. Let me make sure I just understand what you're saying.
Yeah.
The point is, the more modes you add, then at any given time, the better you can fit the signal around that time that you're fitting. But then the problem is that the coefficients of these modes have to be time dependent. And so the region, which you wouldn't expect in the physical process. And so the region over which the fitting works just shrinks to zero.
Exactly.
That's the argument.
Exactly.
I see.
So
Okay,
if your amplitudes depend on time, you're not doing linear black hole perturbation theory. In linear black hole perturbation theory, they have to be constant. And the issue is that you're trying to fit a linear model where it shouldn't be valid. We would expect it to be valid if you go to later and later times, because you're relaxing to the Kerr metric, and the linear perturbation fit should do well. And in fact, it does. But adding the higher modes is overfitting. And let me explain one more time why. Let me give you one more argument. So the other argument is this. What they say in the Gisler et al. Paper is the following thing. Compute the mismatch. Small mismatch means very good fit, okay? So a small mismatch here is a color that is very close to white, and a bad fit is a color that is very close to black. So now you take only the first fundamental mode, and you fit 47M after the peak. You fit 47M after the peak, and with a single mode, you get the right value of the mass and the spin that you can measure from the numerical relativity simulations. But you're 47M after the peak. Then they say, if you fit with only the fundamental mode at the peak, your good fit doesn't even cross the right value. You should include the overtones. I agree with them on this. And in fact, then what do? They add 7 overtones and they say, look, now at the peak, I get the right value of the mass and the spin. Now the question is, did you really need to add 7, right? You could have added less. So you can repeat this game, and we have in a paper in preparation. And what you see here is, do the following thing: fix all of the modes but the nth. And then look for the mass and the spin that minimize the mismatch when you are changing only that mode. Now, you see, when you take the n equals 0 mode, you get a very good fit for the mass and the spin, because most of the information is contained in the n equals 0 mode. Now change the n equal 1. You get a good fit around the true value, but your mismatch is large in a broader region. There is less information in the first overtone, if you like. And as you go on, these regions broaden and broaden up to the point where for n equal 3, they don't even go to the right value. So the n equal 3 mode is not adding any physical information anymore when you fit it at the peak. You see? See what I'm saying? Was it clear enough? So what I'm arguing is that the first mode, the second mode, and the third mode, they give you pretty good information that should be included, but don't go beyond that, because then you're overfitting again. And these are more arguments that I will not repeat because you got the point. But if you randomize over the modes, you're not going to get an improvement when you go to very high overtone number. And you're not going to get a better estimate of the mass and the spin when you go to very high overtone number. If you randomize, you are as likely to do worse as you are to do better. So now the experimental question, we observe the overtones. So what people did in this paper, Max Sisi and others, was they said, well, let's see if adding overtones improves the quality of consistency tests for GW15 or 914. And they took the actual data and they said, this is the value of the final mass and spin that you expect in numerical relativity. This is the value that you will get with only the fundamental mode. But if we add overtones, 1 or 2 of them, we now get a 90% confidence interval on the mass and the spin that is more consistent with the prediction from full numerical relativity. This is just what we would expect, okay? And then they say, this means that we have observed the overtone and we are doing a numerical relativity test. But now look at the corner plot that they have where they show the amplitude of the fundamental mode, the first overtone, and the second overtone. You see that the amplitude of the fundamental mode is definitely away from 0. you have detected a mode here with a non-zero amplitude. But if you look at the amplitude of the first and the second overtone, they rail against zero, which means that you might have detected them, but maybe not, because zero is consistent with the posterior that you get for these amplitudes. They still argue, well, we have observed this mode, and however, in this analysis, I was always very skeptical when it came out because they were fixing also the starting time to a value that was obtained by LIGO. So after a while, I heard this claim over and over again, and we decided to look at the data again. And the main thing that we pointed out was this: you don't know the merger time exactly. You just don't. You have a numerical relativity waveform that best fits your data, and it tells you that the merger occurred somewhere between, let's say, within 1 sigma, the brown, dark brown regions, and within 2 sigma, within the light brown regions. So you can take some time, like they did in that analysis, and you can argue that at that time, the overtones give you a better fit, but you can also take different times. And remember what I said, if you really want to have a linear black hole perturbation theory analysis, you should be something like 10M after the peak. Here I am 2M after the peak. So if I really wanted to be conservative, I should go to times that are so late that the signal in the quasi-normal modes is so weak that you're not going to see pretty much anything. But okay, let's play their game, and let's say we are very close to the peak and we want to fit with more than one mode. Now, what you see here is that if you have a model with only a fundamental mode, you don't quite get a good fit to the in-spiral merger ring-down data. When you include the overtone, you get a better fit, but we don't find as good a result as they do. And let me explain that they were using their own code called Ringdown, and we are using something called PyRing, which is the code that is commonly used by the LIGO collaboration to do this analysis. So we see the same trend, but not as strong. And notice one thing, that the model with the overtone suspiciously becomes a better and better fit to the full waveform when you go to early enough times that the overtone model shouldn't be there at all, because here you are before the peak. So even if you believe the Gisler et al. Argument, your waveform should be a good fit only after 0M and for later times. So then what we did was, here, we took a window and we looked at the posterior for the amplitude that we get. This is the amplitude of the first overtone. And what you see in red is the posterior that we get by analyzing the gravitational wave 150914 data. When you are at times later than 0, your posterior tends to rail against 0. So I wouldn't say that there is a convincing detection of the overtone. You get a convincing detection of the overtone at times before the peak where there shouldn't be any. And this makes us think that probably what triggers this detection of the overtones is noise in the data. So what we did next was we took a numerical relativity waveform consistent with the data and we injected it in different segments of LIGO noise. And what you see are the black lines. So the black lines are injections in zero noise. And we repeated these injections many, many times, and we computed something called the base factor that tells you whether the model with one overtone is favored relative to the model with only the fundamental mode. What we find is that at all times after the peak, the base factor is consistent with 0. And therefore, there is no evidence for the presence of an overtone. You do see an evidence for the presence of an overtone at early times, but that's when you're dominated by noise. Now, there was a response by the authors of the original paper where they repeated the analysis. And here we overplot in green their results. You see that the results are very much consistent with ours at late times. In fact, they realized that they should have done a search for the optimal peak time, and they found that using 2 different models in numerical relativity, the peak time that they estimate is actually later than ours. So if you want to apply a linear analysis, you should be to the right of these green lines, according to them, where the amplitude of the overtone is pretty much consistent with zero. We all agree with that. So I am just not convinced that we have done it yet, and I think that we need better data. It's not that we won't see it eventually, but I think we haven't seen it yet. Okay, now let me argue. How much time do I have? I don't want to run over time too much. This was the.
You're good. You probably have like 5 or 10 minutes.
Okay. Okay. Good. So I will go back to theory again, no data, and you remember the argument by Fermi. If you give me 4 parameters, I can fit an elephant. If you give me 5, I can make it wiggly trunk. Now, there's the famous story of the elephant and the flea. And one question is, when I fit my elephant, is the fit of the elephant stable under perturbations? So if I have a flea and I have a small perturbation of my original potential, is the quasi-normal mode spectrum itself stable? Are the overtones in particular stable? Because maybe it doesn't even make sense to fit with overtones if they are destabilized in realistic astrophysical conditions. There was a particularly illuminating for me study that came out in 2020 by Jose Luis Jaramillo and friends. And what they did was they used a tool called the Pseudo spectrum, which has, as I discovered after their paper, has been used very successfully in many branches of science, including, for example, hydrodynamics. And the theory is very elegant. Basically, what you want to do is you have a spectral problem, generic, doesn't have to be black hole perturbations, and you want to study what happens when you introduce a perturbation on top of the potential. This perturbation can be random or deterministic. And what you want to study is how much the spectrum is going to deviate from the original spectrum, assuming that your perturbation has some amplitude epsilon. So there are 2 ways that you can define this pseudo spectrum, but basically the idea is the following. If you have a spectrum that is stable under perturbations of the potential, then when you introduce a perturbation of order epsilon, you should get contours around the original spectrum that look like this. There should be circles, and they tell you that a perturbation of order epsilon can only displace the modes of the original spectrum by an amount that is proportional to epsilon. If instead your spectrum is unstable, these contours will open up. And so a perturbation of order epsilon can push your original spectrum very far away from the original values of the frequencies. It turns out, as they found in this paper, that the black hole quasi-normal spectrum is unstable, in the sense that when you take perturbations of order epsilon on top of your original potential, the lines are always open. And what they found in this paper is that all of the modes can be destabilized with the possible exception of the fundamental mode. And you start by destabilizing the higher overtones, and then you go down and you destabilize the rest of the spectrum. So we got curious and we said, what's special about the fundamental mode? And so this is a zoom in of what you see. Basically, you see that all of the modes become unstable. And when they are destabilized, they settle along these lines. This is very exciting because it explains some observations that Noller made back in the 90s, where he basically found that if you introduce a stepwise approximation to the original Regge-Wheeler potential, you get a spectrum that is completely different, and it looks like the spectra of W modes in perturbed relativistic stars. I can tell you more later if you're interested, but there's much more.
What is the physical reason that the real part is so much more unstable than the imaginary part?
They are both unstable. They both migrate very far. So basically, the new spectrum that you get when you introduce a perturbation, let me explain a little better what they do here. They introduce a perturbation of order 10 to the minus 8 in amplitude, which is sinusoidal with a wave number k. So what you find is that if you have a wave number that is large enough, say k equal 20, your new spectrum does not look like the original spectrum anymore. You see, for k equal 1, it did. But for k equal 20, your new spectrum is completely different. It corresponds to modes that lie all over the real and imaginary axis along lines of constant epsilon in the pseudo spectrum. You see, the spectrum is completely different. Whether this means something observational is a different question, which we can discuss.
Does this depend on the amplitude of the perturbation?
It does. In fact, you see here that you take perturbations of order 10 to the minus 8, and then you go to the order 10 to the minus 4. The larger the amplitude, the easier it is to destabilize. But for a given amplitude, large K modes are more likely to destabilize the spectrum. So this is very interesting. It's very interesting. And the question is, what happens in a nonlinear merger? Are you destabilizing the higher overtones? How large does the amplitude have to be to destabilize them? We are in the nonlinear regime. A nonlinear perturbation is an epsilon here. And so maybe we don't see the higher overtones because we shouldn't be looking for them, because they have been destabilized by a mechanism like this, you see. So, and the question is, why is the fundamental mode special? It shouldn't be. In fact, what we did was we took a little toy model where this paper is now published in PRL. And what we said was, let's take a perturbation on top of the original Regge-Wheeler potential that decays exponentially. That's because we don't want to disturb the late time tail behavior that is a 1 over r like decay. So we take either a partial Teller potential or a Gaussian of amplitude epsilon at distance a from the peak of the original potential. And then we want to understand, as you change epsilon, which is the amplitude of the perturbation, that's what Shahar was asking, or as we change a, when do we destabilize the original spectrum? And can we destabilize the fundamental mode as well? What we find is similar to results that had been obtained earlier with a simple 2-square barrier potential. In fact, this problem is well known in quantum physics, and it is called the elephant and the flea within that context. So let me show you what happens to the spectrum. I have a nice animation here. Let me explain. So you have a perturbation with a certain amplitude epsilon, and the bump that I have shown you here, let me go back one slide. The bump that I've shown you here, remember, is located at distance a. Now I change a, okay? And you see, I make the bump, I put the bump at larger and larger distance from the original bump of the gravitational potential. Now, the black mode is the original fundamental mode. It's located somewhere here, you see? When the perturbation is small, then you get a mode that is like looping around the original value. But when your bump goes far enough away, what happens is that you are creating a whole spectrum of trapped modes between the left and right barrier. And these are the red dots that you see appearing at the top right. So your black original mode keeps moving, and it moves down, and it moves down, and it moves down. But at some point, it gets overtaken by the red modes that are appearing in between. You see that this mode is now the fundamental one, and then this, and then this. And at some point, you have a jump, and the fundamental mode is somewhere here to the left. So the nature of your spectrum has changed completely, which is exactly what you are observing here.
So can I ask you, it looks like you've introduced like a stable minimum in the potential. Why wouldn't you actually have stuff with negative imaginary parts?
So what you want to ask is, why is this potential positive and not negative?
Yeah, for instance.
So if you, this was one of the arguments by the referee. So if you take, say you take a shell of matter located at distance, say, from the peak, what the shell of matter will do for you is modify the potential exactly in this way. Okay, so this is the realistic astrophysical scenario that you would imagine. Of course, you can play with modifying the potential in different ways and you will get slightly different results. What we wanted to do was introduce a minimal modification and basically understand the phase diagram that tells you when the fundamental mode gets destabilized. What we expect is what we found. It gets destabilized when epsilon is large enough at a fixed day, or when A becomes large. Why? Because remember that the quasinormal mode eigenfunctions in R blow up exponentially. They are not a complete set. In fact, they are not L2. So because the quasinormal mode eigenfunctions blow up exponentially, a bump of the same amplitude located out very far from the black hole is actually more efficient at destabilizing the spectrum.
Yeah, I see. But so just to make sure that I understand the physics, I mean, you're getting degrees of freedom which have a longer lifetime than the original fundamental mode, basically because they can bounce around between these two maxima now. And I was just wondering why that doesn't actually give you an actual instability in the quasi-normal mode spectrum, because normally, like if you did the iconal approximation, but with a minimum in the potential instead of maximum, then you would get.
Yes, yeah, you are right. But this is non-rotating. So this is a non-rotating black hole spectrum. If you do it on a Kerr black hole and you repeat the same game, you could very well trigger a super radiant instability in this way, if that's what you were thinking about.
Yeah. Okay, thanks.
Mm-hmm. And this is an actual plot that shows you what happens. It's the same as the animation before. You see, your spectrum initially is close to the actual value, but then the real and imaginary part fly out, and you get this overtaking phenomenon where if you take different values of A, at some point your original fundamental mode is not the fundamental anymore because it's dominated by these other guys that are overtaking the original one. Okay. Okay, this is everything I wanted to say. I can give you more details if you're interested, but let me summarize. First of all, overtones have long been known to provide a better fit to numerical waveforms. This was understood already in the 70s and 80s for particles falling into black holes, collapse, head-on collisions, and quasi-circular mergers. It was realized immediately after the first simulations in 2005. The question is, should I push this game of fitting with overtones to the points that have been argued recently? And my personal opinion is that no, you're overfitting. What you should do to be conservative is look at the region in time where your amplitudes are still constant. That tells you that linear black hole perturbation theory is still reliable. And in that region, I would trust a no-hair test or a black hole spectroscopy test done with linear modes. But if you want to do a test closer to the peak, then maybe you should look at higher multiples. And higher multiples are excited only for unequal mass binaries. And so far, I don't think anyone would argue that we have really seen that. So I would say that at the present time, there is no convincing argument that we have observed overtones. If we have not observed them, of course, we have not reliably measured their frequencies. It will take higher signal-to-noise ratios and better detectors to be able to do this test in a reliable way. We'll get there eventually, just don't think we are there yet. And the more fundamental question, since I'm talking to mathematicians, is, does it even make sense to fit higher overtones? And I am not convinced. And the reason I am not convinced is that in a realistic astrophysical situation, either accretion disks or matter or nonlinearities within GR in vacuum can be seen as perturbations on top of linear perturbations. And these additional fleas can destabilize the original linear spectrum. Whether this has observational implications needs more work. That's it.
All right, thank you for the fantastic talk. That was super clear. We still have time for questions if so just unmute yourself if you want to ask something.
So, can I ask? So regarding destabilization of the higher overtones. So are you saying that I mean, could it have even implications for observation that we should not try even to fit to some overtone higher than something determined by the effective K and amplitude of the gravitational perturbation?
What I'm saying is that we need to be careful and understand if nonlinear perturbations can be somehow modeled as bumps on top of the original linear potential that destabilize the higher overtones. When we look at the data, what I have tried to show you earlier is that there is really no extra information that is coming from modes higher than n equal 2. So I don't know why that happens, to be honest. It could be because the waveforms are not accurate enough. So at some point, in fact, this is one thing that we're looking at very carefully now. When are you dominated by numerical noise in the waveforms? Another thing that could happen is that there are tails. We know that there are tails in black hole perturbation theory. So maybe I shouldn't be fitting at late times because of tails, but the tails could also be messing up the Ringdown fit at early times. In fact, we are playing with some toy models and we see that this is the case. The tails, if you do have a simulation in black hole perturbation theory at linear level, you do it using Cauchy characteristic extraction, so you don't have to worry about wave extraction effects. And you do it with high enough accuracy. At some point, you still see, let me show you what I'm talking about, because I've been looking at these things for a while now, but maybe you guys haven't. So you see over here what happens at some late time, both in the linear case and the nonlinear case, you see an exponential blow up in the amplitude. Why is it blowing up? It could be blowing up because I'm fitting noise, or it could be blowing up because the tails are taking over at some point. And so we're trying to understand this. And it's also possible that you're messing up the fit at early times, either because of nonlinearities or because of tails, not necessarily because of numerical noise. The SXS simulations are fantastic. I mean, you fit a damp exponential 50M after the peak. That's amazing. In 2007, we couldn't even dream of doing that. Now, the question is, when are we fitting physics? And when are we abusing the overtones to fit something that is either tails or nonlinearities? And what I would argue is that you're getting a bad fit from the higher overtones here, because maybe you shouldn't be fitting them at all. And maybe the nonlinearities are messing up the nature of the higher overtone spectrum. Just don't even go there. You don't even need it for the tests. You only need a couple of modes to do a test.
Thank you.
You're welcome.
Thank you so much for the talk. I really like the history too. That was very interesting. I didn't know a lot of these early papers. So there's a lot of interest nowadays in creating an experiment to look at this photon ring that surrounds a black hole in images. And this is something that could be maybe done in the next 10 years. And I was wondering if there's some kind of statement that can be made about how this relates to black hole spectroscopy, because the gravitational wave experiments are the low L part of the quasi-normal mode spectrum, whereas you can think of these null geodesics as being the approximations to the high L part of the spectrum. Is there some kind of interesting statement relating the measurement of the ring to black hole spectroscopy in this program?
Yes, we've been thinking about it, and we have a paper in preparation about this connection. And I can tell you a little bit about this, but I left it out because I think there's already enough controversy here that I don't want to bring in even more. But yes, so we should be thinking about this more. There was a nice paper by Huang Yang where he was proposing to use the photon ring in conjunction with Ringdown observations. And what he really had in mind, we invited him to JHU to talk about this, but he really has in mind looking at Sagittarius A, say, and seeing the ring down signal from a small object falling into the black hole and then looking. So I think this is honestly not going to happen in my lifetime, because the ring down in an extreme acceleration spiral does not get excited very much. It's just scales like Q squared. So it's going to be very hard to see a ring down from the galactic center black hole. However, there are very interesting ways to think about the connection between the iconal approximation, the quasi-normal modes, and the EHT or next generation EHT tests. And I think we should be thinking about it more. One, I can tell you if you don't scoop me, that one thing we've been thinking about is this. So take the known, for simplicity, start from the spherical symmetric problem. We had a paper a couple of years ago with my postdoc Ryan McManus, Vitor Cardoso, and others, where we said, you can imagine that any modification of GR will give you an inverse power of R correction to the original potential. So that will modify the spectrum in a way that is computable, and we computed it, assuming that all of these 1 over R power series corrections are small in some sense that can be quantified. Now, when you introduce these perturbations that you can think of as a generic parameterization of beyond GR effects, for example, could be matter, could be anything, then you can relate them to modifications of the quasi-normal mode spectrum. But we also know that the quasi-normal mode spectrum is dominated by the behavior close to the peak of the potential. So the parameterization language that we developed for deviations of the quasi-normal mode spectrum, you can also think of it as a parameterized modification of the structure of the potential around the peak. And then you can compute the modes using WKB under different approximations. And you can relate generic beyond GR parameterizations to generic V double prime, V triple prime modifications in the potential. And then those, you can go back and relate them to the geodesic structure. And then you can think of a mapping between what a test of the photon ring tells you and what a test of the quasi-normal mode structure tells you. Now, of course, this is very oversimplified because it's very symmetric. The black holes we see in LIGO, it's spin 0.7. The Kerr spectrum is much more complicated. The geodesics may be non-equatorial. There's a lot of extra calculations to do. But I think we should think about it much more carefully. And eventually, it will be very interesting to map one class of tests onto the other. We're doing baby steps in that direction, but
it's very interesting to point out. You're basically saying when you look at the quasi-normal mode spectrum and you look for deviations from the Kerr prediction, what you're really probing directly are deviations from the shape of the potential in this photon shell geometry. So that's really the thing you're most directly probing.
But is that true? I thought the graph that you
it.
showed us depended heavily on the fact that there was a perturbation actually very far from the peak of the potential. I mean, that would probably give you null geodesics, which sort of bounce between the two, which would give you.
So this is a very tricky point, and I don't want to leave the wrong impression here. Even if you take a bump like the one that I was discussing, when you look at the quasi-normal mode spectrum in the time domain, you still see the original black hole spectrum. This is the whole ECHO program that Vitor and others have been pushing. And the reason is that even if you have that bump, it takes a time that is basically the light propagation time between the bump and the main peak for the modes of the second bump to show up in your spectrum. So if you put the two bumps very close to each other, or, you know, in general, you're going to see modifications both in the initial ring down, but those depend on the amplitude of the bump, and they're only going to get large when the amplitude of the bump is pretty sizable. And then you're going to see the whole trapped mode spectrum, but you will see that after a light crossing time. And so there's two different effects that you can look after. One is the prompt black hole ring down. That only depends on the structure around the peak. And then you're going to see back propagation effects that will appear later. But the reason I never got so much into the whole echo program is that we don't really have any physically well-motivated reason to look at them. I mean, the wormhole scenarios are unstable for other reasons. I don't really believe in gravitational stars. I don't believe in many things. But yeah, so, you know, it's interesting to look for them because if there are modifications of the horizon structure, they will appear. But there are also other effects that you could observe just by looking at what happens around the peak. Mm-hmm.
Yeah, see, that makes sense. Nice.
I have one more technical question, which is in the Psychonal regime, it's you can calculate these quasi-normal mode frequencies analytically,
Mm-hmm.
and you find that the spacing between the overtones, so they're spaced, they have a gap in the imaginary direction, which is integer. It's the same gap between successive overtones.
Mm-hmm.
How do you think about that intuitively? Is there some kind of deep reason?
Yeah. This was, I briefly hinted at this in the very early part of the talk. There was a lot of work on the spacing of the imaginary part of the modes and the asymptotic value of the real part back in 2003, 2004. In fact, that's what revived the whole field in many ways. And people at the time understood the deep underlying reason for this. And it's basically a weak rotation. So what you can do is you can think of black hole perturbation theory in Euclidean time. You make a rotation in time by pi/2. And then what you find is that you can use tools from quantum mechanics to predict that the spacing is basically the period associated with your weak rotated potential by pi/2. This is called the Born approximation, and it's been used. So the real deep reason why you have this spacing is that in the weak rotated potential, you have a periodicity that corresponds to the Hawking temperature.
That's the regime of fixed L and a high N.
Yes.
Right?
Yes.
Yeah, that's the monodromy story. I don't understand the details, but I think, yeah. But it's also true that if you go to large L and relatively small n, that's the Eikonal regime.
Oh,
and
I see.
And there also there's an integer spacing in the ends.
Yes. So in that region, we did some work on this. What you can use is a Bright-Wigner approximation in that case, because you're looking, if you're in the regime of very high L, your real part is much larger than the imaginary part, and then you can approximate the imaginary part as being small, and then you can use these Bright-Wigner resonances to compute the modes, and you can get some additional insight there. But I don't know if this answers your question. I don't want to say anything but I see what you're saying. That's a different regime. You can use different techniques there. The answer that I gave you does apply only to the high imaginary part region. But maybe if you dig
and these are and these are the two, basically, if we take the Schwarzschild black hole, these are the two sort of regimes in which we can compute them analytically, these quasi-normal modes, right?
Yeah.
There's nothing else.
No, not really. Unless you count things like continued fractions as analytical.
Yeah, like Lever's method. I do that in my sleep.
Yeah.
Thank you so much. This was very, very interesting.
All right. Yeah, if there are no more questions, I'll go ahead and stop the recording.